Hi there. Today we're going to be looking at the heat required to change the state of matter, to get through a phase change. If you take a look at this chart here, the phase changes are things like freezing and melting, or boiling and condensing. We're trying to look at how much heat is needed to actually melt something, how much heat is needed to actually boil or vaporize something. That's our focus of today's topic. So, if we're looking at states of matter changes, we better recap the names of them. Now sadly there's new scientific names. I'm sorry. Blame the scientists. Normally when you think of a solid going to a liquid, you would say they're melting. Well, here's your new word for melting. Fusion. Fusion is when you go from a solid to a liquid. Liquid to a solid, reverse. Normally we'd say freezing. Solidification. That one's not too tough. Solidification is your new word you've got to know. Looking at a liquid to a gas, we normally say boiling or evaporating. There are two ways to get there, so we've got a general way, vaporization, to vaporize something. And if we want to go backwards, gas to a liquid, you normally say condense. Luckily for us, we get one of them. Condensation is still it. So here are your new vocab words. If you're thinking, what about the solid to the gas part? It's still the same sublimation. Gas to a solid is still the same at deposition. We infrequently look at those, so I'm not putting them on there. Alright, well we're going to be looking at the amount of heat it takes to get through fusion or solidification or vaporization or condensation, which brings us to a new term. Now it looks like a lot, but let me kind of break it down for you. So if we want to look at how much heat it takes to go through fusion, to have solid ice melt into liquid water, it would be the molar heat of fusion. Oh, this is going to be bad. And we'd symbolize it by just using FUS. That's an F. Doesn't look like it, but it is. The molar heat of fusion has this symbol. The change in H, fusion, equals the molar heat of fusion. The amount of heat needed to, well, fusion is called melting, so melt, oh my goodness, 1 mole of a substance. You can see the blanks that I put in allow us to look at a pattern. So we just looked at the molar heat of fusion, but you can fill in the blanks for any of them. Like the molar heat of solidification has SOL. Molar heat of solidification, a substance, amount of heat needed for a substance to solidify. I think you get the pattern. So although it looks like we've got 4 new things to define, it's really the same pattern again and again. So as long as you know the words fusion, solidification, vaporization, and condensation, you should be fine. So let's actually look at number. We're looking at the molar heat of fusion for water. Water is a classic example. In order to fuse or melt water, you've got to put in 6.02 kilojoules of energy per mole of water that you have. Not a very big number. I know you're looking at kilojoules and thinking that's a lot, but not really that much. So that's how much heat is needed to fuse something or melt it. And if you go backwards, notice it's the same process. So it's the same number, it's just negative. Negative means you are giving away heat. Giving away heat has to be a negative sign. It's leaving the system. In order to make water ice, you have to make it colder. So you have to steal its heat. So if you have liquid water and you steal its heat, then you can make it colder and as ice. The negative value is the idea of stealing heat, negative parts. I want to look closely at what happens when things melt, specifically. Here I've got my ice. When we think about solids, like solid water, it's when one water is right next to another water and they're holding hands. They have a strong intermolecular attraction, and they don't change partners of who they're next to. Intermolecular attractions are strong and set. As a liquid, they kind of move past each other. And that's when they're making intermolecular attractions with the water over here and then some with the water over here. So you can see what we're doing to go from a solid to a liquid is breaking those intermolecular attractions. To melt, you must break intermolecular attractions. Take a look at our first chart that I had up here. Here's your melting and freezing. Take a look at the temperature. We're looking at the starting point to the ending point. The temperature never changes. If temperature doesn't change, that means their speed doesn't change. So if you have solid water and you input heat, it will break its intermolecular attractions and become liquid water. But the speed at which the molecules move hasn't changed. All the energy is going into breaking those bonds, not intra but intermolecular attraction bonds. So the temperature never changes because the speed of which the molecules move isn't changing. But we are inputting energy. You can see that as we move from freezing solid water to liquid water at this corner. This very corner is when it's liquid water, all the way through liquid through here. This very corner is where it's a solid, all the way through here. This in-between part, like midway through, that's like half ice and half water. That's a glass of ice water, and it's at 0 degrees Celsius. Here's a glass of water, right here, of a quarter ice and 3/4 water. It's still at 0 degrees Celsius. If we move it over a little bit, then you're looking at 3/4 ice and 1/4 water, but it's still degrees Celsius of 0. The temperature doesn't change for ice water, whether you've got a lot of ice or a little bit of ice, although it seems funny. It's still at 0 degrees Celsius. Heat is just going to make intermolecular attractions break or make. All right, let's take a look at the next state when we're going from a liquid to a gas. A liquid to a gas we call vaporizing, or backwards is condensing. You can see it's a lot higher in energy, but the same pattern applies. If you vaporize something, it's going to take 40.7 kilojoules per mole input. Liquid has to get hot to become a gas. And if you condense it, then you need to steal heat from it for a gas to become a liquid, and that would be that negative sign. Same number, just plus or minus depending on if you went heat in to make it a gas or take heat out to make it a liquid. Looking back at our same chart, we can see that we have condensing and boiling happening right here. At this corner right here, it is all liquid. At this corner right here, it is all gas. In between, we're half gas, half liquid. That's when you're like mid-boiling. Checking out the temperature, assuming we're looking at water, water boils at 100 degrees Celsius. If you have only a quarter of the pot has boiled, it's at 100 degrees Celsius. If 3/4 of your pot has boiled, it's still at 100 degrees Celsius. Even up to that very point when you have a little bit of water in there, it's still at 100 degrees Celsius. You can't be hotter than 100 degrees until you're a gas. So thinking about what's going on, because we're still inputting heat, we're inputting this much heat to get through the boiling. What the heat is doing is it's not making them move faster. My temperature hasn't changed, so they are not moving faster. Kinetic energy is the same. Speed is the same. The only thing they're doing is breaking intermolecular attractions. The liquid, next to each other, is breaking to become a gas, and gases have no attractions to each other. The heat goes to break the intermolecular forces. All right, I have 2 questions on your Google form. This is the first one. If you take a look at the 2 numbers, 6.02 is much less than 40.7. Why would it take so much more energy to go from a liquid to a gas than just to do a solid to a liquid? That's question number 1. Your other question on your Google form is evaporation endo or exo? You tell me. All right, I'll see you in the next one.